Welcome to solverfy.
In this problem, we have rhinestones that are coated with some material to make them more reflective. So rhinestones are made of glass, so if we zoom in, this is the surface of the rhinestone, and here we have glass. Then there's some coating that has some thickness, D. And we're told this coating has an index of refraction of 2. I'm going to call it N1. And then the index of refraction of glass, we're told, so I'll call N2, we're told is 1.5. So what's going to happen is light is going to hit the surface, and it's first going to hit this front surface, which is the coating, and part of the light is going to be reflected, and then another part of the light will be transmitted and reflect off of the glass surface, so that we end up with 2 reflected rays. And in order for this to be as bright or as shiny as possible, or as reflective as possible, we want these 2 rays, this black and red one, to be completely in phase, which will maximize the amplitude of the light. So that means that the path difference, or the extra distance traveled by this red ray, has to be some multiple of the wavelength of the light. All right, so the extra distance traveled is twice this thickness D, once going to the right and once going to the left. So the extra path length is 2D, and this must equal a multiple of the wavelength. So I'm going to say m, which is an integer of the wavelength, but we have to be careful because it's the wavelength inside this material. So I'm going to say lambda sub n, where n is the index, or refers to the index of refraction. Here we have lambda sub n equals the vacuum wavelength over the index of refraction of the material. Now, there's another thing you have to consider here, is that when you go from a lower index of refraction to a higher index of refraction, the reflective ray gets shifted by half a wavelength. So on this side here, on the left side, the index of refraction is air. I'll call that N naught, and that's just 1. So we're going from 1 to 2 here, index of refraction of 1 to 2. So this black ray gets a half wavelength phase shift. So I got to add plus lambda over 2, and this is still lambda n, because if you're off by exactly a wavelength, well, because this black one gets shifted by half a wavelength, then the whole thing is actually off by half a wavelength. Now it's possible that this back surface will also be shifted, but actually in this case it's not, because we're going from a higher index of refraction to a lower index of refraction, so there's no phase shift at this surface. So we got to add this lambda sub n over 2 here. So in total, what we have is that 2d must equal m and then plus 1/2 times lambda sub n, which is lambda over n1. And they want the minimum distance, so the minimum is if m is 0. So we can set m to 0 and divide by 2 to get that d must equal lambda, where this lambda without the subscript is the vacuum wavelength, divided by, we have a 2 here, we're going to divide by 2, and then we have a 2 from the 1/2 from the phase shift, so that's going to be 4 and 1. And we're told that lambda in the vacuum is 560 nanometers. So plugging everything in, n1 and lambda, into this d here, we find that the minimum distance works out to be 140 nanometers. That's the minimum thickness of the coating.